We discussed symmetry in crystalline solids, which considers the atoms and molecules which form a solid as purely entities in a geometrical arrangement. Apart from this geometrical consideration of symmetry, there is also another important aspect which really determines the nature of a given solid. This is because symmetry describes how the atoms and molecules are arranged in different symmetric patterns in different crystalline solids, but it does not go into why this should be so. In order to attempt to answer this question, it is necessary to go into the detailed atomic or molecular structure and consider the electronic distributions and the interactions between the atoms and molecules, which brings about a certain, which makes the solid a more stable configuration than that of the separated atoms and molecules. The situation here is somewhat similar to that of the formation of molecules from atoms. So, there are situations in which a separate atom is by itself stable, as in the case of, for example, helium or neon, whereas in the case of hydrogen we know it is a diatomic molecule which consists of two atoms together which are bonded together, which is the stable configuration. So, the molecular stability is considered in quantum chemistry. In solids, the forces which bring about the cohesion in a solid is also of fundamental importance. This is what we will consider in this lecture. At first, we will consider the simplest type of solids, which is a molecular crystal. A typical example is that of the solid noble gases or inert gases, such as neon, argon, krypton, xenon. Helium is also in this family, but we do not discuss solid helium. That is because helium, on account of its small mass, is an atom in which quantum effects play a very dominant role, and because of this the helium does not solidify at any temperature above, even at 0 Kelvin. Even at 0 Kelvin, helium remains a liquid unless one applies an external pressure to squeeze the liquid and make it freeze into a solid. So, we will not discuss solid helium, which has somewhat special properties which have to be considered separately. If we leave out helium, these other noble gas solids have all got a closed shell configuration. And because of the closed shells, the attractive forces between the atoms in the solid are rather weak, and they are balanced by strong short range repulsive forces. The bonding mechanism known as the van der Waals bond, the van der Waals forces This usually occurs because of the dipole moment. For example, of a spherically symmetric inert gas atom, for example. If you take a dipole moment of such an atom of polarizability alpha, if the dipole moment of atom 1 is P1, then the presence of this dipole sets up an electric field at a distance r from this atom, which goes as P1 by r cube is the electric field. And therefore, if the polarizability is alpha, if an atom 2 is situated at a distance r from the atom 1, then it experiences a dipole moment P2, which is of the order of alpha P1 by r cube. So, we have now two dipoles, one at P1 and another at P2 equal to alpha P1 by r cube, where r is the distance from atom 1. So, you have the energy of interaction which goes as P1 by P2 by r cube, which is P1 times alpha P1 by r to the power 6. So, we have alpha P1 square by r to the power 6. So, even though in a spherically symmetric configuration the time average dipole moment is 0, but still the square term in P1 which occurs in this energy of interaction between the two dipoles, it is the square of P1 which occurs, and therefore, the square of P1 does not vanish even though the time average of P1 vanishes. So, this is the cause of the weak qualitative picture of the van der Waals force mechanism. Since this has an r to the power 6 dependence, it is rather weak, and therefore, that accounts for the low melting points and boiling points of solid and liquid rare gas atoms. There is a famous potential function known as the Lennard-Jones potential. It is also known as the 612 potential. Is used to describe these weak attractive and strong short range repulsive forces in terms of a potential function which has the form minus a by r power 6 plus b by r power 12. These power 6 and 12 for the attractive and repulsive forces is what gives this the name 612 potential. A and b are positive constants. And r is the interatomic separation, near neighbor separation. This may be rewritten in a dimensionless form as 4 epsilon times minus sigma by r to the power 6 plus sigma by r to the power 12. Sigma and epsilon are known as the Lennard-Jones parameters, and these are given for the 4 inert gas solids in table 1. So, you can see epsilon is given in milli electron volts and sigma is given in nanometers. Using this potential, the energy per particle can be easily calculated. Let us call it U, and that will be just a simple sum over all Bravais lattice vectors. R is a Bravais lattice vector which can be written as a geometrical factor times the near neighbor distance. So, expressing all these Bravais lattice vectors in terms of the interparticle near neighbor distance, then we can express u as 2 epsilon sigma r not equal to 0 A12 sigma by r to the power 12 minus A6 sigma by r to the power 6. Here the ANs, so they can be calculated readily and they are tabulated for the different crystal structures such as simple cubic, body centered cubic and then face centered cubic. They can be calculated because these constants depend only on the crystal structure. And therefore, they can be calculated. These values are shown in table 2 for the 3 different cubic crystal structures. In the case of the rare gas solids, we consider the face centered cubic lattice in which they form. So, the constants A6 and A12 appropriate to the face centered cubic structure are shown in the last column of table 2. The equilibrium near neighbor separation is found readily by setting du by dr equal to 0 by minimizing the energy. So, this leads to the equilibrium interatomic spacing as and substituting for the A12 and A6, this readily becomes, and using this equilibrium value we can calculate the minimum energy of the solid per particle as U0, which is readily calculated to be minus 8.6 epsilon, plugging in the appropriate values of A12 and A6. So, this is something, this interatomic spacing is something that can be compared with actual measured values from say diffraction. Another quantity which is of interest, experimental quantity, is the isothermal bulk modulus. This is defined as minus V and at absolute 0, all our discussions are at t equal to 0 k, when it is considered as a static solid with no temperature effects, P is minus dV, where U is n times U and V is n times small v, where n is the number of atoms in the solid. So, putting all these values together, we can find the equilibrium bulk modulus. For the face centered cubic lattice, we can calculate the equilibrium bulk modulus using V equal to R cube by root 2 for a face centered cubic solid. Therefore, this can be calculated as being equal to plugging in the appropriate values of A6, A12, etc., and this is the equilibrium value. So, this is another thing which can be calculated and compared with the experimental values. We find that this calculation gives correct values more or less in agreement between theory and experiment for xenon and krypton. It gives the experimental values are 20% higher than calculated values for argon and 60% higher for neon, indicating that these have 0 point contributions. So, that gives a brief idea of the forces which are responsible for formation of a molecular crystal such as a solid noble gas atom. A very similar approach can also be adopted in the case of ionic solids. Ionic crystals are ones in which there are ions such as sodium plus and chlorine minus, forming sodium chloride. So, the sodium plus and the chlorine minus ions are arranged regularly in the crystal lattice of sodium chloride, and it is their mutual interaction, electrostatic interaction, which gives rise to the net stability This is the attractive electrostatic potential, with R being the near neighbor separation, and the repulsive part of the potential, we know that it is not as short range as R to the power 12. So, we let it be some m, where m is found from comparison with experiment, and we can perform the energy per ion pair can be calculated by summation over all the ion pairs in the crystal lattice of n ions, and these lattice sums which give you the total contribution are governed by the so called Madelung constant, which depends only on the structure of the crystal lattice, and for NaCl it has the value 1.748. So, using the Madelung constant and plugging in this expression and summing over the n by 2 ion pairs and minimizing the total energy for a face centered lattice with a basis of two oppositely charged ions, we can obtain the equilibrium near neighbor separation as R naught to the power m minus 1 equals Bm by A square, where A is the Madelung constant. So, that is one experimental parameter that one can determine, and therefore, using this you can calculate the constant. The equilibrium lattice energy corresponding to that becomes U naught equal to minus just like in the case of the molecular solids, we can also calculate the equilibrium isothermal bulk modulus, which again is an experimentally accessible quantity, and the equilibrium bulk modulus can be calculated and it can be compared with the experimental values and for the ionic solids, a comparison between the experiment and theory sets the limits for the values of m between 6 and 10. With that, it is possible to find reasonable agreement between experiment and theory. In contrast with this situation for an ionic crystal, there are other types of solids which are known as covalent crystals. Diamond is a typical archetype of a covalent solid. As we all know, diamond consists of nothing but carbon atoms, which are bonded in a tetrahedral configuration inside a cube. The point group symmetry appropriate to this is known to be TD. This covalent crystal is characterized by an appreciable delocalization of electrons. If one compares the X-ray diffractogram of an ionic solid with that of a covalent solid, one will find that the electronic density peaks are exactly situated at the sites of the ions with very little electron density in between the ions. Whereas, in the case of a covalent solid like diamond, the electron density between the carbon atoms is found to be appreciable, indicating the considerable degree of delocalization of the electronic charge. So, such a situation is most conveniently described by the theory of molecular orbitals. For example, the simplest prototype molecular orbital theory, which explains the formation of a covalent bond which binds atoms together to form molecules, is based on an approximation known as the LCAO approximation. LCAO is short for linear combination of atomic orbitals. For example, if you consider the hydrogen molecular ion H2 plus, so that we have a single electron in the potential of the two nuclei due to the two hydrogen atoms, the two protons which are designated as A and B. So, you have various terms. The Hamiltonian consists of the potential of the electron in the fields of these two nuclei. So, the electrostatic potential can be readily written to form the Hamiltonian of the system, and we write the wave function, the molecular orbital, as a linear combination Ca psi A plus Cb psi b, where Ca and Cb are constants to be chosen to minimize the energy. So, with such a wave function, the expectation value of the energy can be calculated So, if we plug in the expression for psi, we get something like Ca square HAA plus Cb square HBB plus Ca Cb HAB divided by Ca square plus Cb square plus 2 Ca Cb times S, where HAA, for example, is the matrix element of the Hamiltonian H between the wave functions psi A and psi A. Similarly, HBB is psi B H psi B, whereas HAB is psi A H psi B, and S is known as the overlap integral. Between psi A and psi B, and is defined as psi A psi B, the product. So, minimizing this energy with respect to minimization of E with respect to variations in the variational constants C A and C B leads to equations, a couple of equations which have the form and solving these two simultaneously means that the determinant of the coefficient should vanish, and that gives us a quadratic equation. In the simpler case of a homonuclear diatomic molecular ion such as H2 plus, we can set HAA equal to HBB and get E as the minimum energy. This leads to a quadratic equation. So, it will have two roots, one with a positive and another with a negative sign. So, I have E plus minus. So, this will be HAA plus or minus HAB by 1 plus or minus S. If this, the plus sign corresponds to Ca equal to Cb, so that we can choose psi as psi A plus psi B with a 1 over root 2 for normalization, whereas the minus root the other root has this solution. So, that this is an antisymmetric linear combination. It turns out that the original energies which are the same, which are degenerate in the case of the separated atoms, hydrogen atoms. Now, in the presence of the interaction, there are two energies. Now, the degeneracy is lifted, the energy is lowered in one case and the energy becomes higher in the other. This is known as a bonding orbital, and this is the anti-bonding. So, this corresponds to the symmetric linear combination, the bonding orbital, and so it piles up the charge between the two atoms. And the anti-bonding, which is an excited state, corresponds to the antisymmetric linear combination. So, the covalent bonding piles up the electronic charge between the atoms and therefore maximizes this overlap integral. The essence of covalent bond formation is that it corresponds to a configuration in which the overlap between the atomic orbitals is maximum. Now, when we come to diamond to discuss the case of diamond, we find that it has a tetrahedral configuration. So, the overlap to find the linear combination of the atomic orbitals of the carbon atoms involved, the carbon has the electronic configuration 1s2, 2s2 and 2p2. One s2 of course is a closed shell. So, it is the 2s2 and 2p2, 2 electrons in the s shell and 2 electrons in the p shell of the carbon atom. These are the ones which are, these are the atomic orbitals which are involved in the covalent bonding. In order to maximize the overlap between them, it is necessary to consider the symmetry of the spatial arrangement of the carbon atoms, which as we know corresponds to a tetrahedral TD symmetry. So, the reducible representation of the point group, this point group TD for the 4 orbitals is given, can be readily found these are the various symmetry elements. And the reducible representation for this, for the 4 orbitals, can be easily found So, this reducible representation can be broken up into irreducible representations which correspond to the symmetry. Therefore, these irreducible representations can be readily shown to be A and T, A1 plus T2. So, that means that A1 is a one dimensional irreducible representation for which the basis is that of an s orbital, and T2 is a 3 dimensional representation which has the basis Px, Py, Pz. So, the symmetry adapted LCAO, linear combination of the atomic orbitals, should conform to this situation of an s orbital and 3 p orbitals instead of 2 s orbitals and 2 p orbitals. So, the symmetry adapted LCAOs, linear combination of the atomic orbitals, corresponds to a situation in which, say, one of the s electrons in the 2s shell is excited into the p orbital. So, that we have 1 electron left here and 3 electrons in the 2p shell. So, these occupy, this corresponds to an s orbital, and these have now 3 orbitals with px, py, pz. So, you can form linear combinations of these. Since there is an s orbital and 3 p orbitals, it is known as the sp3 hybrid. This phenomenon is known as hybridization, and this hybridization has the consequence that the overlap between these wave functions are maximum, making for single covalent bonds for all the 4 orbitals concerned, in which the lobes pointing along the tetrahedral directions. So, that is how we have the sp3 hybridization in the covalent solid of diamond. So, this gives the diamond its stability because of the sharing of the electron charge in a covalent bond. Just like the carbon, there are other solids in which there are sp2 hybrids. An s orbital and 2 p orbitals can form in a plane at angles 120 degrees, and this is what happens in, for example, graphite, where sp2 hybrids are formed and there are layers with covalent bonds in the plane, and then there are weak van der Waals forces between the layers. In addition, you have a pz orbital which is with one electron perpendicular to the plane containing the sp2 hybrids. So, the overlap between the neighboring pz orbitals gives you a pi bond. So, this contributes to additional stability of materials like graphite. The sp2 hybrids can also form a closed spatial network, such as in the fullerene, which has a 60 carbon atoms in a kind of buckyball configuration containing 12 pentagons and 20 hexagons, which form a closed spatial structure. So, these are the various interesting solids in which covalent bonding plays a major role, with appreciable delocalization of the electron density. An extreme case of this delocalization occurs in the case of metals. The metallic bond corresponds to extreme delocalization of the electrons, valence electrons. So, you have the metallic bond in which the valence electrons or conduction electrons are free to wander. So, throughout the crystal lattice within say a square well potential. So, the free electron approximation satisfies the behavior, is satisfactorily able to describe the behavior of electrons in metals, provided we take into consideration the Fermi-Dirac statistics, which is obeyed by electrons. Apart from all these solids, there are other interesting classes of solids, such as the hydrogen bonded, which is the principal source in, for example, solid ice. The water molecule has 2 hydrogen atoms, and each hydrogen atom is covalently bonded to the oxygen atom, and then it forms also a bridge to a neighboring oxygen atom belonging to another water molecule. So, there is an extensive hydrogen bonded network. So, thus we have covered the entire gamut of different types of bonding mechanisms which bring about the cohesion in solids, and this is a very topic of great importance to bear in mind when discussing solids of different kinds.